So today we are going to be solving Cambridge O-Levels Chemistry Multiple Choice Paper 1 May June 2025 and Paper 12. So let's get started with this paper. The first question states that at temperature X, the volume of sample of hexane and pentane are not affected by changing the pressure from 1 atm to 2 atm. Okay, so what you're doing is, this might seem a bit complicated, like what's happening, but you simply have a sample of hexane and pentane. You don't need to know the formulas, just you have a sample of hexane and pentane, and you increase the pressure from 1 atm. For instance, it was initially 1 atm, and now you move the piston downwards and you increase the pressure. But increasing the pressure has no effect, is not affecting the from 1 atm to 2 atm. Even if you increase the pressure, that's not affecting the sample of the gas. Okay, this sample of gas or liquid or solid, whatever it is, that's not being affected by changing the pressure from 1 atm to 2 atm. We know one thing for sure, that gases are always affected by changing pressure. When we increase the pressure, the volume of the gas decreases. That is what we know. So if hexane and pentane are not being affected by changing the pressure from 1 atm to 2 atm, they definitely either be liquids or they might be solids. We don't know. Okay, next says at temperature X, the pentane molecules are free to move. When we know that they're free to move, then we know one thing, that molecules can only move freely in liquids. In solids, molecules are in fixed position, they cannot move freely. So definitely pentane is gonna be a liquid at this temperature. Now talking about next thing, that's hexane. At temperature X, the hexane molecules are in fixed positions. Okay, so they are in their fixed position. So we know that molecules in solid are in fixed position. So it's gonna be option number A, which is gonna be correct. I hope that makes sense. Next question states a gas is produced by a chemical reaction at one side of the laboratory. Okay, so for instance, over here we have a test tube and we are doing some experiment, and we basically produce some gas. Okay, so these are the gas particles. Over here the gas is produced. After a few minutes, okay, the gas is detected at the other side of the laboratory. After a few minutes, the particles, they're going to travel, and the gas particle, they're detected on this side of the laboratory. Which process explains, okay, so now over here the examiner asks, which process explains why the gas is detected on the other side of the laboratory? Over here, where it was produced, the gas particles were in higher concentration. Over here, on this side of the laboratory, the gas particles were in lower concentration. So particles move from an area of higher concentration towards an area of lower concentration. When particles move from higher to lower concentration, that's simply diffusion. So the answer is going to be option number B, which is diffusion, particles diffusing from here to here. Next statement says, which statement is correct? All compounds are ionic. No, they can be covalent, they can be giant covalent, they can be different, they don't have to be specifically ionic. All compounds conduct electricity when molten. No, we know that giant covalent, apart from graphite, they don't conduct. We know simple covalent don't conduct. So statement B is wrong. Next statement says each atom of an element contains the same number of protons. Yeah, this statement is correct, that each atom of an element, if an atom belongs to a single atom, for example, if you talk about lithium, so though lithium has isotopes, for instance, I say lithium 6 or lithium 7, these are two isotopes of lithium, but though lithium has isotopes will have different number of neutrons, but the proton number in an element, a single type of element, the proton number is the identity of that element, and it always remains same in that element. So it's going to be option C, which is going to be correct. That's definitely correct. Okay, D says in a mixture of substances, the proportions of substances are always the same. No, in mixtures you can vary the proportion. That's good thing for mixtures. For example, I give you an example of a for instance, I say I have a salt solution. Salt solution is a perfect example of a mixture. You can vary the amount of salt in it. You can add as much salt as you want. So in mixtures, you can vary the proportions. Okay, atoms of element Q form positive ions. Okay, if they form positive ions, it's going to be Q and positive something, positive 1 or positive 2 or positive 3 or whatever positive. Okay, an ion of Q has 10 electrons and 14 neutrons. Okay, so an ion, after losing electron, this Q, after losing the electron, it's gonna have 10 electrons. So an atom of Q, for instance, this is an atom of Q. It's gonna have a different number of electrons, and an ion, this is an ion of Q. It has 10 electrons, okay, and 14 neutrons. Okay, an atom of Q has only 2 occupied electron shells. How do you know? It does not has 2 occupied, it has 3 occupied. How do I know? Because look, 10 electrons after losing 1 electron or 2 electron or 3, it has 10 after losing. So initially we believe that it had more than 10. An atom of Q, initially, first shell, here we go with the second shell, and here we go with the third shell. An atom of Q initially had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Initially it had maybe 11, maybe 12. An atom, we're talking about an atom, not an ion. And after losing these 2 electrons, okay, after basically letting these 2 electrons go off like this, now it has 10. That means initially, before forming this Q positive ion, it had more than 10. It had 11 or 12 or 13. And after forming the ion, now it has 10. So before that, the atom had more than 10. So it had more than 2 occupied electron shells. Q is a non-metal. It's gonna be a metal. It's forming a positive ion. It's basically losing electrons. The atomic number of Q is 10. How can it be 10? After losing 2-3 electrons, it has 10 electrons. Okay? I told you initially it's gonna have more than 10. So initially, let's draw it that it's gonna have more than 10. There's gonna be a third shell around it, something like this, which I told you guys, and there are gonna be 2-3 electrons in that shell as well. I don't know how many that it's gonna lose, but the atomic number of Q cannot be 10, because after losing electrons, it is 10 electrons. That means initially there were more electrons. That means initially there were more protons. And if we talk about atomic number 10, we're talking about neon, and we know neon cannot form this positive ion. The mass number of Q is greater than 24. We know this. That's going to be definite. How? Because I know it had more than 10 electrons. How I know an atom of Q had more than 10 electrons? Because it lost how many electrons? It lost 2, 3, 4 or 1 electron, and now it has 10. So initially the atom had more than 10. So if it had more than 10 electrons, that means it had more than 10 protons as well. So if I add this, I get 24. Electrons plus neutrons is 24. And I know protons were also there. Protons, I'm not adding the protons, but I know that initially the proton number, it has to be more than 10. So my atomic number is gonna be more than 24, which makes, not atomic number, sorry, it's gonna be the mass number, which is gonna be more than 24, which makes option D the correct answer. I hope you get it. This was a little trickier question, but I guess not that difficult. Which particle contains the greatest number of electrons? Okay, so it's gonna be this. Why this? Because look, magnesium, it basically has 12 electrons, and forming a 2+ ion, it's gonna lose 2 electrons and it's gonna have 10 electrons. Nitrogen, initially it has 7 electrons. After gaining 3 electrons, 3 negative ion, it's gonna have 10 electrons. Neon atom has 10 electrons. And if we talk about a sulfide ion, sulfur initially has 16 electrons, and after gaining 2 electrons, 16, 17, it's going to have 18 electrons. So the most number of electrons is going to be in sulfide ion. Okay, the table about 2 isotopes in a sample of an element of europium is shown. What is the relative atomic mass of this sample of europium? Okay, so we have to find the relative atomic mass. Now we have the relative mass of the isotope and we have the percentage abundance. It's simple, it's easy. We just have to multiply this with this thing, this with this thing, and then add them. 150 multiplied by 47, it's going to be 150 multiplied by 40, 150.92. Okay, you have to be careful about the significant figures. 150.92 multiplied by 47.81, and then we're gonna add in it the mass of the other isotope, which is 152.92 multiplied by 52.19 upon the sum of two abundances. In this case, since it is percentage, so it's going to be 100 upon 100. So just put this thing into my calculator. Okay, 150.92 times 47.81. 150.92 times 47.81 plus 152.92 multiplied by 152.92 multiplied by 52.1919, whatever this gives me, divided by 100, I get 151.9638. So this is my answer. Now let's see which one matches. This one matches. Option number B. You don't have to round it off. You have to give it in the number of significant figures. If someone tries to round it off and think it's 152, he's probably going to select option number C, which is wrong. You have to select option number B. Don't round it off. Okay? Don't round off your answer. Which statement about magnesium oxide is correct? It is a high melting point and a good electrical conductive RTP. No, not at all. This one's correct. It has a high melting point. Yeah, it has. But good electrical conductive at RTP, at room temperature and pressure, magnesium oxide is a solid. Why is it's a solid? Because magnesium oxide is a ionic compound, and you know ionic compounds, they don't conduct in solid. Why they don't conduct? Because the ions are stationary. Ions cannot move from their fixed position. Okay, it is made up of magnesium anions. No, magnesium cations. Magnesium ions are positive ions. They are known as cations. It is an ionic compound and has good electrical conductivity in molten. Yeah, that's going to be correct. Ionic compounds, good electrical conductivity in molten state because ions are able to move. It is strongly bonded because if electrons are not shared in ionic compounds. Electrons are transferred in ionic compounds from one atom to another. Okay, which statement about silicon IV oxide is correct? Okay, silicon IV oxide, what we're talking about is a giant covalent structure, which is SiO2. So basically we're dealing with a giant covalent structure. We have to keep its properties in our minds. Okay, it conducts electricity. No, it does not conduct electricity. It does not has any free electrons that are going to conduct electricity, so no. It is a giant covalent structure. Yes, it is going to be a giant covalent structure. It is an alloy. No, it's not an alloy. We're not talking about brass or bronze. They're going to be alloys. It's ionically bonded. No, it's covalently bonded. Okay, which compound is has the highest relative formula mass? Okay, to find the highest relative formula mass, we first need to derive the formulas. For calcium carbonate, for that you got to be good with charges. For calcium carbonate, it's going to be CaCO3. For lithium sulfate, it's going to be Li2SO4. For magnesium chloride, it's going to be MgCl2. For potassium nitrate, it's going to be KNO3. So over here, someone did not know that lithium has a +1 and sulfate has a -2, and this comes down here and this comes down here. He'd probably be like not getting it correct, or magnesium has a 2+, or chloride has a -1. This comes down here, this comes down here. That is why it's MgCl2. Probably be doing it wrong. Okay, now we have to calculate the mass of each one of them. Okay, for this one, it's going to be 40 plus 12 plus 16 times 3. For this one, it's going to be lithium is 7, I guess. Yeah, 7 times 2 plus sulfur is 32 plus 16 times 4. For magnesium chloride, it's going to be 24 plus 2 times 35.5. For KNO3, you have to calculate for all. There's no like substitute for hard work. For nitrogen, it's going to be 14 plus it's going to be 16 times 3. Let's first calculate for this. 40 plus 12 plus 16 times 3. Okay, 40 plus 12 plus 16 times 3, it gives me 100. So this is gonna be 100. 7 times 2 plus 32 plus 16 times 4. 7 times 2 plus 32 plus 16 times 4, and that gives me 110. Okay, 7 times 2 plus 32 plus 6. Okay, 24 plus 71. That gives me a 95. I don't know if I'm making any silly error. Kindly correct it in the comments if I'm making. NO3, so it's gonna be 39. N is 14. O3, 16 times 3, it's gonna be 101. So it's 101. Okay, so let me check one more time for lithium sulfate. If I've not made any mistake, Li 2SO4, yeah. Lithium is 7 plus 7, S is 32, SO4, 16 plus 16 plus 16 plus 16, that's 110. So it's going to be option number B, which is lithium sulfate, 110, has the highest relative formula mass. Yeah. Okay, 100 cm cube of ethane is completely combusted in 400 cm cube of oxygen. What's happening? You have ethane, you are combusting it in oxygen, and the volumes of both gases are measured at RTP. What is the final volume of the gas in the mixture measured at RTP? Okay, so now there's one important thing at RTP. RTP means room temperature and pressure. So what's going to happen is that the first thing, let's write down the equation for ethene, which is C2H4. C2H4 plus, you have your oxygen, you're forming carbon dioxide and your water, and you're gonna use 2 moles of this, 4 moles of this. No, not 4. They're gonna be 2 moles of this, and 2 2s are 4 oxygens. Now we have to balance, plus 2 equals to 6, so there's going to be a 3 here. Done and dusted. Okay, so now we have 100 cm cube of ethene. You see the molar ratio, there is 1:3 between ethene and oxygen, 1:3. So if we have 100 of ethene, we're going to need 300 oxygen. If you didn't understand, just reverse it and listen it again. There is 1:3 between ethene and oxygen. So if we have 100 ethene, we need 300 oxygen, but over here we have 400 oxygen, so 100 cm cube is going to be left behind. Okay, 100 cm cube is unreacted oxygen. Okay, so we write that there's going to be unreacted oxygen, which is going to be 400 minus 300, which is equals to 100 cm cube. Okay, this is unreacted oxygen. Now let's find out the volume of carbon dioxide. We don't need the volume of water. Why don't we need? Because at RTP we are only finding the final volume of gas in the mixture, and you know at RTP water is a liquid, not a gas, so we only need oxygen. So if we were doing like, if this is 100, this was 300, oxygen is going to be 200, so it's simply 200 cm cube of oxygen is going to be formed, and it's easy peasy, lemon squeezy. This is going to be 200 cm cube, 100 cm cube of this oxygen is left, 200 cm cube of carbon dioxide is being formed, so it's going to be 200 plus 100, which is 300 cm cube. If someone thought that water would be a gas at room temperature, then he might have selected option number D, which I don't think is correct. Okay, the formula of hydrated sodium carbonate is this. What is the percentage composition by mass of oxygen in hydrated sodium carbonate? Okay, so what do we have to do? We have to find the entire MR of this thing, which is gonna be 23 plus 23 plus 12 plus 16 times 3 plus 10 times 18, because that's of one water. 10 times 18 is for 1 water, and times 10 because we have 10 water. Okay, we have to find the percentage by mass of oxygen. Okay, so below we're gonna have this in the denominator, so let's take this entire thing. Okay, put this in the denominator. Okay, this is gonna be our denominator, and the numerator is going to be the mass of oxygen. What's going to be the mass of oxygen? How many oxygens we have? We have 3 oxygens over here, 3 oxygens in this thing, and 10 oxygens in water, plus 10, so that's 13. So 13 times 60 and multiplied by 100. Okay, so now let's see first what do we get in get below. Okay, Na2 23 plus 23 plus C plus O3 plus 18 times 10, and that gives me 286 in the denominator. 286 upon 13 times 16, 13 times 16, 208. 208 times 100, 208 divided by 286 multiplied by 100, that gives me 72.7%. 72.7%. I hope you get it. Okay, the diagram shows the electrolysis of molten lead bromide with inert electrodes. Okay, so the diagram shows the electrolysis of molten lead bromide. Okay, it's molten. Firstly, it's molten. Molten means that, what does molten mean? That we only have lead ions and bromide ions. We don't have any water. So we have Pb2 plus ions and Br -1 ions. Okay, so now which one identifies the particles that carry charge along each row? Okay, you know one thing for sure, that over here, this one's the positive electrode. The positive electrode, which ions are going to be attracted, bromide or lead? Positive is going to be attracted to negative ions. So over here at 3, the ions that are basically coming towards this part are going to be bromide ions. So we know that for 3 we are going to have bromide ions. Okay, now we need to figure out what's going to be at 4, lead ions or electrons. What's going to be at 4? It's going to be electrons. What's happening over here is that, look, at your anode, oxidation is happening. These bromide ions that are coming over here, I'm going to explain this process to you. I hope you guys get it, that, look, there are going to be some bromide ions, -1, that are going to be coming here. And these bromide ions that are coming at the anode, they're going to basically lose their electrons. 2 bromide ions are going to lose 2 electrons to form bromine liquid or bromine gas. So what's happening is that these bromide ions are losing electrons. So over here, when they lose their electrons, the electrons, they basically move up. You know how electricity is being conducted over here? The bromide ions, when they lose electrons, the electrons move like this to over here. And over here, at the negative electrode, the electrons are added to Pb ions. Pb2 plus ions are deficient of 2 electrons. So the 2 electrons that these bromide ions lost over here are added to this lead ions to form Pb solid. Do you get it? So at 4 we're definitely going to have electrons. So at 4 we're going to have electrons, at 2 we're going to have electrons, at 1 we're going to have electrons. So 4, 1, 2, it's basically the movement of electrons. Okay, so which makes option number C the correct one. Okay, what are the products formed when two electrodes add the two electrodes when aqueous copper 2 sulfate is electrolyzed using copper electrodes? Okay, so what are we doing? We have aqueous copper 2 sulfate, and we have aqueous copper 2 sulfate. That means we have Cu2 plus ions, and we have SO4 2 negative ions of copper and sulfate, and for water we have H plus ions and we have OH negative ions. Okay, so now we need to think what's going to get discharged. Firstly, out of these two ions, which is more unreactive, copper or hydrogen? We know, if you know the reactivity series, please learn hydrogen is above copper. So what's going to get discharged? Definitely copper. So cathode product is going to be copper metal. It cannot be hydrogen because hydrogen is above in the reactivity series. At the anode, sulfates and nitrates, they don't discharge. So at the anode, what's going to discharge? Your hydroxide is going to discharge. And when your hydroxide discharges, you form oxygen gas. So it's going to be option number C, which is going to be correct. Okay, which statement about hydrogen oxygen fuel cell is correct? It uses a chemical reaction. It uses a chemical reaction that is only one product. That's correct. You basically have hydrogen, you have oxygen, and the one product you form. So what is a hydrogen oxygen fuel cell? You might think of it. It's basically H2 plus O2 forming H2O, you put a 2 here, and you put a 2 here. So basically that's the entire thing that's happening in your hydrogen oxygen fuel cell. So I think it's correct, but let's see, there might be a better option. It works by burning hydrogen in the air. No, you don't burn it in the air, you add oxygen to it. It requires a continuous input of electrical energy, not electrical energy, there's a chemical energy required. This oxygen is not electrical energy, it's chemical energy. It is less efficient than petrol. No. This releases much more energy than your petrol. So I guess it's going to be option A. Reaction pathway diagram is shown. Okay, reactants are below, products are above. You need to realize one thing, please. I say that realize it. When reactants are below the products, okay, products are above, reactants are below, you should know that this is definitely gonna be which kind of reaction, exo or endo. This is gonna be an exo. No, not exo. This is gonna be an endothermic reaction. Okay, this is gonna be endothermic. Which reaction equation shows this? Endothermic means that you give heat energy. So you need to give the heat energy to break the bonds. Okay, to break bonds. So which equation does the reaction pathway diagram show? Definitely not A. Why not A? Bonds are being formed in A. Look, you have 2H and you have O, and you're forming H2O. No, bond formation is exothermic. We need an endothermic. We need to break bonds. Okay, definitely B. It's going to be option number B. Why it's going to be option number B? Because look, bonds are being broken in B. What bonds are being broken in B? Look, in B you have H2, something like this, and then you break this bond to form 2H. Get it? Over here you're breaking bonds. In C, you're converting a gas into a liquid. When you convert a gas to a liquid, what happens? Energy is being released from the gas. Gas particles are more energetic. They are more energetic than a liquid particle. So they have to release some energy to convert into a liquid. So definitely not C. D, again, bonds are being formed. They're not being broken. We need to break bonds because bond breaking is endothermic and bond making is exothermic. Okay, which process is a chemical change? Okay, chemical change, the rusting of iron, 100% chemical change. Why? Because it is irreversible. You can't get the iron back. Okay, the melting of wax, that's a physical. You can convert it back into a solid. The evaporation of water, again physical. The distillation, these are all three physical processes. This one's a chemical one. Okay, aqueous sodium thiosulfate reacts with HCl. Okay, the rate of the reaction increases if the concentration of both reactants is increased. Okay, so obviously you can increase the rate if you increase the concentration of both the reactants. Okay, next statement says nitrogen gas reacts with hydrogen gas. The rate of the reaction increases, the pressure in the reaction vessel is increased. Okay, which row correctly explains why the change increases? Okay, so if you increase the concentration, there is going to be higher frequency of collision. So increasing concentration, what does it mean? It means that you have a beaker and initially you just had these many particles, but when you increase the concentration, what are you doing? You're increasing the number of particles. And when you increase the number of particles, what do you expect? By increasing the number of particles, what's going to happen? Now I increase the concentration, I increase the number of particles. See it for yourself. What effect does increasing particles has? Now there are going to be more collisions. Why? Because there are more particles available. Initially there were less particles. So increasing concentration basically increases. Why would it increase the activation energy? Not the activation energy, just the number of particles. So increasing number of particles means that there's going to be a high frequency of collisions. So A and B. Okay, and increasing the pressure, again higher frequency of collisions. Why? Because look, when you're increasing the pressure, what are you doing? You basically have this reaction vessel and you have these 3-4 particles over here, and you have a piston over here. So now if you increase the pressure, what are you going to do? You're going to move the piston downwards. When you move this piston downwards, what's going to happen is that these particles are going to be compressed like this as you move the piston down, and when they're going to be compressed, their volume is going to reduce, and when their volume is going to be reduced, the piston moving downwards, the volume is going to reduce, there's going to be more frequency of collisions between the particles. The activation energy, it has nothing to do with pressure or pressure or this concentration thing. Okay, activation energy can only be changed by one thing, and that's a catalyst. So it's going to be option A, that frequency of collision between the particles increases. Okay, magnesium reacts with dilute sulfuric acid. Okay, you know, you have magnesium, you have sulfuric acid, and you can form magnesium sulfate and H2. Two experiments are carried out at 25 degrees Celsius. Experiment 1, you have 24 gram of powdered magnesium with 100 cm cube or 1 mole per dm cube sulfuric acid. Okay, so now you need to realize one thing, that you have some magnesium and you have sulfuric acid, so you can find the moles of magnesium as well as sulfuric acid as well. So you would have to find which one is the limiting reactant over here. In the next experiment, you have 24 gram of powdered magnesium reacted with 50 cm cube of 2 mole. Okay, so now doubling the concentration and halving the volume. Okay, doubling the concentration and making the volume half of sulfuric acid. Okay, during which experiment the volume of the hydrogen gas produced measured at regular time intervals, the results is plotted. Which graph is correct? Okay, first things first, equation shows that 1 mole of this reacts with 1 mole of this. Okay, so we need to find out the moles. Okay, so first let's find out the moles for magnesium. It's going to be mass over mr. So the mass of magnesium is 24, the mr of magnesium is 24, so we have 1 mole of magnesium. How many moles of sulfuric acid we have? Simple, moles equals to concentration times volume. Concentration is 1 times volume is 100, but since it's in cm cube and we need the volume in dm cube, so we multiply it by 1000. So it's going to be 1 times 100 divided by 1000, and that gives me 0.1. Okay, so the concentration of the moles are going to be 0.1 moles. Okay, over here we have 0.1 moles and over here we have 1 moles. This means our magnesium is in excess, as far as I guess. Over here as well, magnesium is going to have 1 moles. Over here sulfuric acid, let's see, 50 into 50 volume here divided by 1000 times 2, 50 divided by 1000 times 2, that gives me again 0.1 mole. So over here both my acid is my limiting reactant in both reactions, and since the amount of the limiting reactant, the moles of the limiting reactant determines the moles of the products, so in both experiment I'm gonna have the same amount of hydrogen gas. So over here I have different, in option number C and D you can see I have different amount of hydrogen in both experiments, so cross. For experiment 1, experiment 2, I should have the same amount of hydrogen, so it can either be A or it can be B. Now I need to see, over here I have in experiment 2 there's only one thing, I have double the concentration, and you know when you increase the concentration the rate of the reaction increases. So for experiment 2 I'm expecting a higher rate of reaction, so experiment 2 is gonna have a higher rate. Over here I can see experiment 2 has a lower rate because the gradient is lower. Over here the gradient is more steeper, so experiment 2 should have a higher rate, otherwise the product is going to be same, which makes option A the correct one. Okay, which one gives the catalyst for each of the two processes? Okay, I don't need to explain this contact process. It's simply going to be vanadium oxide. For Haber's process is going to be iron. You need to learn these things. Okay, the diagram shows the changes in pH as a strong alkali is added to a weak acid. Okay, so you have a strong alkali, you're adding it to a weak acid, and the concentration increases like this. Not the concentration, the pH increases. The volume of the strong alkali, as you increase the volume of the alkali, the pH increases, and then the pH becomes constant, though you're adding more volume of the alkali. 40 cm cube of a strong alkali is added to a weak acid. Okay, and the sample of the solution is tested separately, and the sample of the solution is tested separately with methyl orange and thymophthalein, which was correct. Now at the end you can see that your pH over here, what is the pH? It's approximately it's 12. Okay, so that's going to be an acidic pH. Over here we have approximately a 12 pH, so that's not acidic, sorry, that's going to be an alkaline pH. Okay, so this one's an alkaline pH, so methyl orange is going to turn yellow, and thymophthalein in alkalis is blue, so it's going to be option number C. Do you get it? What's happening over here? They just added some alkali. The pH chart is something like this. At the end the pH of the solution is 12. you add indicator to it, you see a yellow color on this because methyl orange is yellow in alkali and thymophthalene is blue, which shows the equation for the dissociation of methanoic acid and nitric acid. Okay, over here what's happening is that acid is being dissociated. Now one thing you should know, that methanoic acid, this is a weak acid, and weak acids ionize partially. So this is the sign for partial ionization. This is a sign for full ionization. So it's either going to be option C or D. And HNO3 is not a weak acid, so this partial ionization is not going to happen for HNO3. There's going to be a full ionization for HNO3. So it's going to be option number, this is correct, option number D is going to be correct. Okay, which statement about elements in the product table is correct? Across a period, elements at the left hand side of the product table are more metallic than those at the right hand side. No. Yeah, at the left. Okay, so let's just see the product table. So this is the product table, something like this, and over here we have the metals. Okay, and at this side we have the non-metals. Okay, so this one's the left side and this one's the right side. Okay, now it's gonna be easier. Across the period, elements at the left hand side of the product table are more metallic. Yeah, over here we have metals, so they're more metallic. Yeah, down the group, elements at the top of the group lose electrons more readily. No, as you move down the group in metals, the reactivity of metal increases, and when the reactivity increases, they're going to lose electrons more readily. Okay, elements in the same groups of the periodic table, same group, have the same number of complete electron shells. No, elements in the same group, they have the same number of valence electrons, not the electron shells, the valence electrons. Okay, now elements in the same period, they have the same number of outer shell. No, they have the same number of electron shells. In same period you have the same electron shells, in same group you have the same valence electrons, or the outermost electron. Okay, rubidium and cesium are elements in group 1. Okay, you should know that cesium is above rubidium. Okay, which prediction comparing rubidium and cesium is going to be correct? Cesium has a higher density and greater reactivity. No, down the group density increases, down the group reactivity increases. So rubidium has more density, has more reactivity. Cesium has higher density, no, it has lower. Rubidium has higher density, yes, and greater reactivity, yes. Rubidium is going to have higher density and greater reactivity because in group 1, what happens down the group? In group 1, when you move down the group, your reactivity increases and your density also increases down the group. So rubidium is below cesium. Okay, 3 statements about halogens are listed. All halogens are non-metallic diatomic molecules. All halogens are non-metallic. Yeah, they're non-metallic. They're diatomic molecules. Yeah, sure, they're diatomic. Because if you look at halogens, fluorine F2, Cl2, Br2, I2, all are 2. This small 2 over here shows that they are diatomic. Correct? Option 2 says chlorine displaces bromine and iodine from aqueous solutions of the salts. Yeah, chlorine is going to displace both of them. Why? Because you should know that a more reactive halogen is gonna displace a less reactive halogen. Displaces a less reactive halogen. So consequently chlorine is going to displace both of them. Okay, the halogens become more reactive on descending group 7. No, descending means going down. They become less reactive, so it's going to be 1 and 2, which makes option B. Okay, which statements about neon are correct? It is unreactive. Yeah, it's a noble gas. It's going to be unreactive. It is strong intermolecular. No, it has weak intermolecular. It is non-metallic. It's on the right side of the periodic table. It is a gas. Gases have weak intermolecular force of attraction. It is a full outer shell of electrons. Yeah, that's why it's a noble inert gas, because neon is gonna have how many electrons in the last shell? They're gonna be complete 10 electrons in the last shell, something like this. So this is neon. It has complete shell, so it's gonna be 1 and 3 only. Okay, substance X has the following properties. Okay, melting point high, boiling point high, malleable, good electrical conductivity. This is definitely gonna be a metal. giant metallic lattice. Simple. Which statement explains why objects manufactured from aluminum corrode very slowly? Because it has a layer of aluminum oxide on it. Okay, so if this is aluminum, this blue one is aluminum. So if you basically have an object that's made up of aluminum, it's gonna have a layer. This red layer is aluminum oxide, and this red aluminum oxide layer is gonna be impermeable. This Al2O3 layer, it's not gonna allow the oxygen and water to corrode the surface, so, or any other substance to corrode it. Aluminum is above hydrogen. No. Coated with a protective layer of aluminum nitride, not nitride, aluminum oxide. Okay, the iron 3 oxide is used in the blast furnace, contains impurity silicon IV oxide, which reaction removes silicon IV oxide. This one. You have your SiO2, you have your calcium oxide. How did you get calcium oxide? You got calcium oxide from the thermal, you remember, decomposition of your limestone that you added, which was calcium carbonate. You remember, you had your calcium carbonate and it basically decomposed into calcium oxide plus carbon dioxide, and this calcium oxide reacted with the silicon oxide to form calcium silicate. So that's the reaction that's happening over here. Okay, the domestic water supply is treated before it is supplied to houses. Their treatments are listed. Sedimentation, filtration, that's going to obviously remove solids. You're filtering something. How can it kill microbes? Filtration, simply what it does is, this is your filter funnel, this is your beneath something, and over here all the solid insoluble particles are going to settle over here, and that's going to remove solids. Okay, treatment with chlorine kills microbes. Remember this, chlorine is going to kill microbes. Treatment with carbon, what carbon does, it basically removes the smell, or you can say the odor in your water. So removes unpleasant tastes and odors. That's going to be option number B. Okay, nitrates and ammonium salts are used as fertilizer. Okay, that's what we know. Which fertilizer contain the greatest mass of nitrogen, 50 kg of the compound? Okay, so first you need to find the amount of nitrogen in 1 kg, and then you can find with in 50 kg. Okay, so let's try to do it. Okay, now how much nitrogen this compound contains in its 1 kg, and then we're going to find for 50 kg. Okay, we're going to do something like this, the ratio method we're going to use. So that's basically 14, that's the mass of nitrogen, divided by the total mass of this compound, which is going to be we'll find the percentage composition. Obviously that the compound which has the highest percentage composition of nitrogen is going to have the greatest amount of nitrogen in 50 kg. So 14 plus 4 plus 35.5, let's see what this gives. Okay, this one, second one is going to be 14 plus 14, because there are two nitrogens upon the total mass, which is going to be 14 plus 14 plus 4 plus 16 times 3 times 100, just times it by 100, times it by 100. This one right here, this one is going to be 2 nitrogen, so 14 plus 14 upon 14 plus 14 plus 8. Remember, you have 8 hydrogens, 4 2 times 8. Okay, so plus 32 plus 16 times 4 times 100, KNO3, it's gonna be, I guess it's gonna be KNO3. I just guess. No, it might be KNO3. No, it's gonna be option number A. Okay, let's find out. Let me not guess it, because if I start guessing, you guys are also gonna start guessing, and that's not good for you guys, because in exam it's why risk your grades. Times 100. Okay, we've already done it. Okay, so we're gonna find for each one of them. Okay, 14 plus 4 plus 35.5, 14 plus 4 plus 35.5, that's 53.5. 14 divided by 53.5 multiplied by 100, that's a 26%. By mass, it's nitrogen. Over here, okay, 14 plus 14 plus 4 14 plus 14 plus 4 uh, plus 16 times 3, 80. 28 divided by 80 times 100, that's a 35%. Okay, for this one it's gonna be 14 plus 14 plus 8 plus 32 plus 16 times, let's check if I remember. 14 plus 14 plus 8 plus 32 plus 16 times 3 times 4 tha. It was 16 times 4. 4 and 28 divided by 132 multiplied by 100, that gives me a 21.2%. And KNO3 for 39 and 16 times 3 and 14. 39 plus 14 plus 16 times 3, and that gives me 101. 14 divided by 101 and times 100, that's a 14% biomass. 14% biomass. So now we have the percentage composition biomass of nitrogen. We know that if we take 50 kg of this, it's gonna have 26% nitrogen. If we take 50 kg of this, it's gonna have 35%. And if we take 50 kg of this, it's gonna have this. And if we take 50 kg of this, it's gonna have this. So according to this, I guess that option B can yield more nitrogen. Okay, which strategy reduces methane emissions? Obviously methane is produced by the livestock farming. You should know that the waste gases in animals, they release methane gas. So reduction in livestock farming. Compound P is an alcohol with a molecular formula this. How many structural isomers are there of compound P? Okay, structural isomers, we need to draw them. C4H10O, but1ene, but2ene, and that's all. Sorry, butane 1 all, butane 2 all. So C4 OH can be on the first carbon like this. Remaining H we have to draw like this. Doom. And over here, look, there's OH is on the carbon 1. So this is butane 1 all. But what if we make this OH on carbon number 2? Something like this. So we erase it from carbon number 1 and we make this OH right here on carbon number 2. Now this is butane 2 all, because OH is on the carbon number 1, carbon number 2. So this is butane 2 all. So these are the only two structural isomers that are possible. So it's going to be option number A. Okay, because you might think, I know what comes in mind, that this OH could be made to carbon number 3 as well. But if we move this OH to carbon number 3, what's going to happen? We're going to start the counting from the other side. So it's going to be 1, 2, and then it's again going to become butane 2 all. And if we move it to the last carbon, we're going to start the counting from here. It's going to again become butane 1 all. Okay. Alkenes undergo substitution reaction with chlorine. Okay, that's what we know. They're going to undergo substitution reaction with chlorine. Which wrote two correct statements about the reaction between alkanes and chlorine. Okay, so we have alkanes and we have chlorine. A carbon atom is replaced by a chlorine atom. No, a hydrogen atom is replaced. So what basically happens in this reaction is, you should know this thing, that you have an alkane. For instance, you have CH4 like this, and you add chlorine to it. So what basically happens is that this hydrogen is basically so this hydrogen over here is basically replaced by a chlorine. So chlorine moves here, hydrogen moves here, so we basically form HCl and something like this. This is chloromethane whatever. Okay, so that is what's gonna happen over here. So now this requires activation energy that's provided by UV light to basically break the Cl-Cl bond first. So the reaction requires thermal energy? No, not thermal energy. The reaction requires ultraviolet light, and hydrogen atom is replaced, making option D the correct one. Okay. A molecule of compound C4H6 is shown, okay. One molecule of C4H6 reacts with dash molecules with dash of bromine. One molecule or two molecule. Okay, so what do we need to do? We need to, over here, what do we need to do? What do I need to do? I need to break this bond, attach one bromine here, and break this bond, attach one bromine here and one bromine here. Okay? How many molecules? 4 atoms of bromine I need. One molecule of bromine has 2 atoms. I need 4 atoms. So I need 2 molecules of bromine. Okay? And when C4H6 reacts with steam, dash is formed. An alcohol, okay, it's an alkene. And you should know that alkene plus steam equals to your alkene, and addition of steam, catalytic addition of steam forms alcohol. So it's gonna be option number C. Which statement of the members of a homologous series of alcohols is correct? An alcohol with 2 carbon atoms in each molecule is called methanol. No, it's called ethanol. Butanol can be combusted to give carbon dioxide and water. Yeah, that's correct. You can combust any alcohol to give you carbon dioxide and water. Ethanol is the only alcohol that can be oxidized into carboxylic acid. No. You add an oxidizing agent to butanol like KMNO4, you're going to form butanoic acid. If you add to ethanol, you're going to form ethanoic acid. Propanol can be made by the catalyzed addition of steam to ethene. Not ethene, by the catalyzed addition of steam to propene. Propene plus steam is going to make propanol. Ethene plus steam is going to make ethanol. I hope you get it, okay? The diagram shows the structure of a compound called ethanoic anhydride. Okay, so this is ethanoic anhydride. 1 mole of ethanoic anhydride reacts with water to form 2 moles of a carboxylic acid. Okay, so 1 mole of this compound is going to react with water to form 2 moles of a carboxylic acid. So what's going to happen is basically that this bond is going to break from here, okay? One H is going to attach here, and OH is going to attach over here. So now you have 2 moles of your acid, okay? I hope you're getting. This is 1 mole of your acid, and this one is the second mole of your acid, okay? Number of moles of water. How many moles of water we just used to break it down? We just used 1 mole of water. We used H2O. Easy peasy lemon squeezy. So we're going to use 1 mole of water. And the structure of the ester. Okay, what was about the ester? How many moles of water react with 1 mole of anhydride, and what is the structure of the ester? 1 mole of ethanoic anhydride reacts with form this carboxylic acid reacts with ethanol to form an ester. Okay, so now what kind of carboxylic acid are we forming? We're forming a carboxylic acid above and below with 2 carbons. So this carboxylic acid is ethanoic acid, and this is also ethanoic acid. So ethanoic acid, now this acid is going to react with ethanol. So ethanoic acid plus ethanol. So what is going to be the ester? You have your ethanoic acid and you have your ethanol. So what are you going to form? You're going to form ethyl ethanoate. And what's going to be the formula of ethyl ethanoate? 2 carbons for the ethyl, 2 for the ethanoate, making option A the correct one. Okay, 4 samples were analyzed using paper chromatography. PQR are pure substances. Okay, PQR are pure substances. We know them because they have single spots in the chromatogram. M is a mixture of different substances. Okay, M contains Q, M contains P, M does not contain R. Which substances does M contain? Okay, we just figured out M contains P. And why does M contain P? Because same line. Why does M contain Q and P? Because same line. So P and Q only. So it's gonna be P, Q and another substance. Yeah, not only another substance is also present at the top, this other substance which is unknown. So P, Q and another substance. Okay. A student is making a sample of aqueous copper to sulfate. Okay, the student adds an excess of copper oxide powder to warm sulfuric acid and stirs the mixture. The apparatus is used to separate aqueous copper to sulfate from the excess copper oxide. Filter, funnel and filter paper. What are we doing? We're simply removing the excess of copper oxide. Initially we had a beaker, we had sulfuric acid H2SO4 in it. We added some copper oxide to it, which was CuO. This was added in excess, and when we added it in excess, some of it reacted, and when some of it reacted, some was left behind. So some will react and some will be left behind. Now this part of it that's left behind, we need to get rid of it. So what we're gonna do, we're gonna take a beaker like this, we're gonna put a filter funnel like this, and we are gonna pass this mixture through this filter funnel. What's gonna happen, the copper sulfate is gonna be collected at the bottom, CuSO4, and this unreacted copper oxide is gonna be collected on the top. Why did we take it in excess? To make sure all the acid would react, so that in this no acid is left, all acid reacted, only this is left, which is copper oxide. Okay, so filter funnel and filter paper. How can a pure sample of barium sulfate be obtained to form barium carbonate? Okay, first we need to obtain a pure sample of barium sulfate. We obtain from barium carbonate. Okay, barium carbonate, is it soluble or insoluble? What do you think? Definitely it's gonna be insoluble. Okay, and barium sulfate, it's also gonna be insoluble. So now we need to make this barium carbonate, add this barium carbonate into something that's soluble, because when we make salts, we cannot use an insoluble reagent. So dissolve it in HCl. Very good, because when we dissolve our barium carbonate, this is insoluble. From this we cannot make barium sulfate easily. How? Because this is also a solid and this is also solid. We need the barium ions in a aqueous solution. So what are we gonna do? We're simply gonna take barium carbonate, add HCl to it, gonna form barium chloride, which is aqueous. Barium chloride is a soluble salt. And now we can take this barium chloride, make it react with sulfuric acid. So what's gonna happen next? We have our barium chloride, BaCl2. We're gonna make it react with sulfuric acid and form BaSO4 and plus HCl, 2 moles of HCl. So now we're gonna form this thing, and since this is insoluble, this is a solid, insoluble, we're gonna filter it and crystallize. Do we crystallize the insoluble salts? We're gonna filter and simply wash. So it's gonna be option number B. We cannot dissolve barium carbonate in water. This is completely wrong. Why? Because it's gonna be insoluble in water. Okay, the last question finally says a sample of white powder X is dissolved in water. Okay, so we have a sample of white powder. We're going to dissolve it in water. Tests are done on separate portions of the solution, and the observations are shown in the table. Test. Add aqueous sodium hydroxide to a drop at a time until excess white precipitate forms soluble in excess, giving a colorless solution. Okay, so either this can be a zinc ion or an aluminum 3+ ion, because both give white precipitates that are soluble in excess of NaOH. Acidify with dilute nitric acid and add aqueous silver nitrate, white precipitate. With silver nitrate, you add silver nitrate. What's going to give a white precipitate? If you have your chloride ions, they're going to form AgCl, and this AgCl is basically your white precipitate. So it's going to be chloride ion. So it's going to be chloride, and acidify with dilute nitric acid, then add aqueous barium nitrate, and the solution remains colorless. Now, what kind of ions are we talking about? Look, the ions that we're talking about over here, because the solution remains colorless, that means there is no sulfate ions. Because why are we adding barium nitrate? We add barium nitrate to check the presence of sulfate ions. So definitely it's going to be aluminum chloride. No calcium does not give precipitate, and no sulfate. So done and dusted. I hope you liked the video. Do consider subscribing to the channel, and that's gonna mean a lot.